in UG's group. And most of the results you're going to see today were obtained in collaboration and together, in fact, with the group members you see listed in front of you. So this is really in the name of the whole group. And the talk is going to be kind of a journey taking us from the most massive stars down to surprisingly low mass stars. And I try to hold the talk so that it targets a broad public of astronomers. I hope it won't be too trivial for most of you. And if you have any questions, of course, feel free to ask after the talk. So the talk starts with this guy here called LB1. Which late last year caused a lot of havoc because it was reported to be a binary in our own galaxy that contains a 70 solar mass black hole. And it was published in Nature, and it did cause a lot of excitement also in our group. And soon thereafter, the media went all over it, reporting of an impossibly massive black hole. Now, I want to stress that all the black holes I'm going to mention today are stellar mass black holes. So these are black holes that come from stars. And in the next few slides, I'll try to explain why 70 solar mass is such a big surprise, especially in our own galaxy. Much more recently, a few months ago, there was another system called HR 6819 that was claimed by Revinius et al. To be a triple system consisting again of a black hole. This time it's not the most massive black hole, but it's because of the distance to the system, it turns out to be the nearest black hole to the sun. And again, the media really likes these kind of titles. So you could find in the newspapers all over that astronomers found the nearest black hole to the sun. And we'll get back to this system as well towards the end of the talk. So why do we keep hearing so much about black holes all of a sudden? I guess most of you are aware of the fact that we are, in the last few years, detecting gravitational waves for the first time with the LIGO and Virgo interferometers. And these gravitational waves are coming to us from the very distant universe, from merging events, such as the one you see here, of black holes or neutron stars. And one of the exciting things that we can do with gravitational waves is by direct means measure the masses of these objects. And one of the more impressive outputs of this gravitational wave physics is a diagram such as this one, where on the y-axis you see the mass of a compact object, and the x-axis has absolutely no meaning. It's just a bunch of events. And down here are the neutron stars. Up here are the black holes. You see there is a gap between them. And before we had gravitational waves, the primary way to detect the mass of a compact object was by finding them in X-ray binaries. So in binaries where a compact object would accrete matter from a nearby star. And you can see the sort of masses one would get for neutron stars and black holes by doing that. Ever since the detection of gravitational waves, what happens is that we're starting to populate this upper part of this diagram. So you basically see every time two black holes that with two arrows pointing into one black hole, so that's a merging event. And there is a lot of physics to discuss here. For example, the fact that all these masses are significantly higher than we've observed before. But I would like to draw your attention especially to one fact, and this is that if you look at all these events, you will find that none of the black holes seem to exceed a mass of about 50 solar masses. You do see black holes that are more massive than this limit, but these are always merged products. The original black holes do not exceed this limit. Well, this was correct up to a few weeks ago. For the first time, a gravitational wave event was reported that actually exceeds this limit. And the masses are given here. This is a big surprise, and it's still not understood by the community and still needs to be verified. So I will, for the remainder of the talk, kind of ignore this event and focus on the fact that for now, the vast majority of targets did not exceed the limit of 50, and you'll soon see why we think that is the case. So to understand this mass distribution and why it's so surprising to find a 70 solar mass black hole in our galaxy, we need to remind ourselves where black holes actually come from. And they come from the cores of massive stars. So these are stars that are start their lives with at least 8 times the mass of the sun. And we define this seemingly arbitrary limit because we think that stars more massive than this would end up developing an iron core and eventually undergo a core collapse, leaving behind a neutron star or a black hole. They are very rare stars because of the initial mass function, which tends to, or which favors the production of low mass stars. And they're also very rare because they live a very short life. So while stars like our sun live over the scale of billions of years, massive stars evolve over the scale of millions of years. But they make up for the rarity by being extremely luminous. So one massive star can outshine 1 million suns in terms of how much energy it produces every second. And they also tend to be very hot, meaning that their energy, the energy that they emit, is very intense. Massive stars are also characterized by powerful, radiatively driven stellar winds. So what is a stellar wind? It's basically an outflow of the material that is at the surface of the star away from the star. And radiatively driven means that this outflow is driven by the absorption of light of the star itself. And this is an important thing we'll talk about later, and which induces mass loss on the star. Finally, massive stars end their lives, most massive stars end their lives as core collapse supernovae, which are some of the most powerful explosions that we know in the universe. And to understand massive stars from birth to death, we usually use this tool here. In case you're new to astronomy, you should probably know it. It's called the Hertzsprung-Russell diagram. It's a diagram we often use to discuss the evolution of stars, where you see the luminosity versus temperature. And here you see an example for an evolution track of such a 15 solar mass star that would look like an early B-type star. It would spend, like all stars, most of its life on the main sequence, burning hydrogen, until eventually it would leave the main sequence and would become a red supergiant, where it initiates core helium burning. And eventually, red supergiants are expected to explode as hydrogen-rich supernovae, leaving behind neutron stars. But something quite different happens as you climb up the mass ladder. If you go to even more massive stars, say O-type stars, instead of ending their lives as red supergiants, these stars tend to end their lives as very hot, hydrogen-depleted stars. The reason they do that is because they have such a strong mass loss that they can actually strip themselves off their outer layers, and we see deep into the hot, hydrogen-depleted core of the star. And we recognize the equivalent of red supergiants, so the hot part, the evolved massive star, very massive stars, are called classical Wolf-Rayet stars. These are stars that are indeed hydrogen depleted, hot, have very powerful stellar winds, and are thought to be the progenitors of black holes. Now, this is just a slide, a commercial slide for massive stars, because I will be talking mostly on black holes and related things, but massive stars actually have a gigantic impact on the environment, and you can just see that by taking pictures in the local group, which you see in front of you. So these pictures are completely dominated by the content of massive stars within them. So whether it's through their winds and supernovae and hard radiation, they completely dominate the stellar feedback. They enrich their environments with heavy elements, and they also enable us to study of extreme physics. So there are a lot of reasons why we care about these rare objects. But in the context of black holes, if we want to understand why a 70 solar mass black hole is surprising, the obvious question to ask is how massive can stars actually get? And the obvious way to answer this question is to take a telescope and try and find the most massive stars out there. And measuring the masses of stars is not easy, especially as they get massive. And one of the most reliable ways to do that is through binaries. And people have been doing that, and doing that in the Milky Way, in these two clusters, the record-breaking stars currently reach masses of the order of 120 solar masses. So we know that stars as massive as 120 exist in our galaxy. If we leave our galaxy and go, for example, to the Large Magellan Cloud, a nearby galaxy, then there are even more massive stars that were reported, one of which we're currently working on, with robust masses of the order of 140 to 150 solar masses. And this is currently considered the robust upper mass limit on stars. It doesn't mean that more massive stars don't exist, but we haven't detected them by direct means. In fact, right in the Tarantula Nebula in the Large Magellanic Cloud, there is a cluster, very dense cluster called R136. And in the core of this cluster, colleagues were able to actually resolve the core to individual objects that you see here. And especially A1 and A2, these two kind of sources here, if you just look at how bright they are and what kind of temperatures they have, and you compare this with evolution models, you find that these look like 300 solar mass stars. The problem is that it's not clear yet whether or not these are truly unresolved stars, whether there are unresolved stars in here or whether they're truly single stars. This is something we're currently collecting data with the Hubble Space Telescope to try and figure out. So hopefully we'll have more constraints on these stars. So 300 solar mass as an upper limit is well possible in the local group, but it's not as robust as 150. So why am I telling you all of this? Well, if we know that such massive stars exist, why is it so surprising to find a 70 solar mass black hole in our own galaxy? Why does it get published in Nature? And the obvious answer is that, at least for stellar astrophysicists, is that stars lose mass. And we know that even the sun, this is a real video of the solar outflow, the only star where we can actually resolve the stellar outflow. We know that the sun loses mass through its wind. But the mass the sun loses per year, so we usually measure it as solar masses per year, is puny. It's only 10 to the minus 14 solar masses per year. If you multiply this by the solar lifetime, which is about 10 to the 10 years, you get a number that is 10 to the minus 4, so a fraction of a percent, meaning that if the sun will always keep losing mass at its current rate and always has, then it would have only lost about a fraction of a percent of its mass, which is negligible in terms of its evolution. However, as you do this exercise to more massive stars, taking 200 solar masses as an extreme, even though they live much shorter lives, their mass loss rates can be up to 10 orders of magnitudes larger. And so if you do this exercise, you can actually get to masses that exceed the initial mass, which of course cannot be true, but it comes to show that mass loss becomes an increasingly important driving mechanism in the evolution of stars as you climb up the mass ladder. And you can see that just by looking at evolution tracks. This is an example for a 120 solar mass star evolution track calculated with the BPAS code. And down here, you see the evolution of the mass. So you see that the star starts its life with about 120 solar masses. It loses quite a lot of mass already on the main sequence, which lasts about 2 million years, but then enters this Wolf-Rayet phase, where within a very short amount of time, it loses about 80% of its mass. And the fate of such a star is to end its life with about 10 solar masses. So it's very hard for these stars to retrain their original mass. And this is directly confirmed by observations of such Wolf-Rayet stars. Recall that these are the evolved products of the most massive stars. And we can see these stars, we can see them in binaries. These are stars that I also spent quite a lot of time working on. And you can try and measure their masses. It's not an easy task. Here you have some non-published distribution that I would not want to publish because it's an unhealthy mixture of different populations. But it just comes to show that the typical masses of these stars are between 10 and 20 solar masses. So nothing like the original 100 solar mass star that they may have started their lives with. So if this is correct, and the most massive stars end their lives as 10 or 20 solar mass stars, how can it be that we see 50 solar mass black holes with gravitational waves? Well, it has been soon realized that it's related to something we call the metallicity. So the events, the gravitational wave events that we see in the very distant universe come to us from regions that are not yet enriched in heavy elements, because these heavy elements come from stars, massive stars, and low mass stars as well. And we call these regions low metallicity regions. What does it mean for a massive star to be born in a low metallicity environment? Well, its layers are going to be less opaque because these heavy elements are a very important source of absorption, of opacity. And this means that these stars are not as efficient in absorbing their own light and driving a stellar wind, which means that massive stars in a very distant universe are going to have much weaker winds and are going to be able to retrain significantly more mass as they evolve. And you can again see that by comparing on the left a galactic 120 solar mass star, and on the right you see the same 120 solar mass star, but calculated for a low metallicity environment, a fifth of the solar metallicity, which corresponds to the small Magellanic Cloud. And you can see that according to this model, at least such a star would not end its life with 10 solar masses, but rather with 40, which makes a big difference if we want to understand the mass distribution of black holes. All right, so if we can use metallicity to crunch up the masses of black holes, maybe this is the explanation for the 70 solar mass black hole. Maybe it originated in some weird low metallicity environment. So the first problem is, of course, that this star, this LB1 is right in our own galaxy. It's not too far from the sun. Why should it form in such a low metallicity environment? But there is an even more fundamental problem with forming 70 solar mass black hole, which is completely related, and I'm only going to touch upon that. And it's related to pair instability supernovae. So the idea is that stars that somehow manage to end their lives with about 60 solar masses are expected to undergo a type of explosion which is called pair instability supernova. And one of the special characteristics of the supernova is that they don't leave anything behind. The entire star becomes a gigantic explosion, so they don't leave black holes behind. And in fact, detailed models suggest that on this basis, you do not expect to see black holes that are more massive than about 50. Any star that somehow manages to end its life with a larger mass would undergo this apparent stability supernova. And so you can start to see why it was such a big surprise to see a 70 solar mass black hole in our own galaxy. And there was a series of papers, first of all, discussing why this is a problem and portraying the problems with the detection of LB1, and also trying to suggest alternative models, what could be wrong in our theory to explain the formation of the 70 solar mass black hole. I'm not going to enter these papers. Instead, I'm going to focus on what we did. We as observers in KU Leuven were more interested in actually understanding whether these results are actually reliable and what were the data on which they were based. And so let's reiterate for a second. LB1 is, like I said, a galactic star. Nobody heard anything about it before it was reported to be a 70 solar mass black hole. It's about 2.1 kiloparsec away from the Earth. It's neither too bright nor too faint. And it was discovered by the Lamoste survey and published by Liu et al. In Nature to be this binary. Now, Liu et al. Claimed this binary to consist of a B-type star, something that looks naively like an 8 solar mass star, which they claimed is an 8 solar mass star, and going around in a binary orbit of about 79 days around a black hole. The black hole mass, like I said, is 70. That's what they claim. The orbit is basically circular, and the black hole has a disk around it. This is what Liu et al. Claimed. So what were their results based on? So most of you probably know that when you take spectra of a binary system, as the two stars go around one another, you would see the spectral features of the two stars moving back and forth in antiphase, like you see in this cartoon here. And by measuring the motion and the velocities with which these stars move, we can constrain the masses of the two objects. And this is precisely what you see in the case of LB1. So these are real data taken with our home telescope, Hermes. And yeah, you can see here, even if you're not a spectroscopist, I'm sure you can appreciate the fact that there is a feature here moving back and forth. This feature belongs specifically to the helium-1. And you can go ahead and measure the velocities, the radial velocities associated with this feature, the Doppler motion, and you get this red point here that is moving. And you can see that it traces this nice radial velocity curve that indeed has a period of about 79 days. Now, if you look at the whole spectrum, it indeed naively looks like an 8 solar mass star, like a B-type star. This is what the authors thought as well. And there must be something causing the star to move back and forth. A star doesn't just move like this on its own. And you look at the spectrum and you don't really find another star that moves in antiphase behavior to this one. But you do see something else, which is very peculiar. This is the age alpha line, a line belonging to the hydrogen Balmer series. And for a normal star, you would just expect to see absorption, just like this absorption here. You would expect to see absorption moving back and forth with the same period and behavior. Instead, you see this crazy emission that seems to have a life of its own. Now, for a spectroscopist, this emission is very suggestive of the presence of a disk. This line is very susceptible to outflow, and the shape of this line looks like there is a disk in the system. The authors of the Nature paper noted that the wings of these lines, if you, and I try to focus on them here, this is really hard to see, but if you really try to focus your eyes, you may be able to see that every time the absorption line is on the right, the emission moves ever so slightly to the left, and vice versa. So they noted that the emission and absorption seem to move in antiphase to one another. And what they said is, well, this emission comes from some kind of a disk around an unseen companion. This companion moves in antiphase to the star that we do see, the visible star, and therefore it must be around the companion. So they tried and measured the velocities associated with these motions. This is taken from the paper. And you can see the radial velocities of the visible star, which I call here the B-type primary, and the unseen companion, which is this emission feature, which is associated with the disk, which moves much more slowly. Now, by measuring the amplitudes of these motions and the ratio, you can actually calculate immediately calculate the mass ratio of the two objects. And by doing that, relying on their measurements, the authors concluded that the mass of the unseen object that has a disk around it must be around 8.5 times the mass of the object that we do see, the B-type star. Like I said, they naively attributed it as an 8 solar mass star. You'll later see that this is not correct, but this was the author's results. And by plugging in 8 in this equation, you get that the mass of the unseen object must be around 70 solar masses. Now, if it were a star, a 70 solar mass star would completely outshine everything in the system. So it's definitely not a star, and the only object we know of that can be so massive and not emit light is a black hole. So this is what the Nature paper was basing its results on. So where are the problems? The first problem has to do with the fact that with the interpretation of the motion of the emission feature as actual motion of the disk. And to illustrate this, I remind you that in this age alpha line, where we see emission, we actually expect the normal star to show absorption, like I mentioned before. And this is actually a real model of such a star. Now, it's kind of an exaggerated example, but the star would be moving back and forth with its corresponding velocity. And now imagine that you have, for some reason, static emission that does not move in any way. If I add up these two signatures and I would observe such a system with a static emission and a moving absorption that looked like this, I would get these kind of blue simulated spectra that I added some noise to make them more believable. You can see if you look at the wings of the line that it looks like the emission is moving in antiphase. Every time the absorption is on the right, the emission seems to move to the left and vice versa, exactly like you and I were observing. We know that nothing is moving here, and this realization was actually suggested for the first time by Michael Abdulmasih, who is my colleague. I'm sure most of you know him. We were all sitting together in the seminar room where he suggested that this could be a potentially very important thing we need to account for, and we immediately simulated this, and we saw that indeed this was a very important realization. So this was, we basically prepared within 24 hours reply paper in Nature, and on the same day it was also published by an independent group. The main conclusion is that we cannot trust the mass ratio between these two components. So because the measurement of the velocities of this emission cannot be trusted, we don't know what the mass ratio between the two components is. But the problem continues and becomes even worse when you actually perform a detailed spectroscopy of the star that you do see. And 3 different groups, including our own, have done that. And we all find, independently of one another, that the star that we do see, the visible star, does not seem to have an 8 solar mass, does not seem to have 8 solar masses, but rather 1 to 2 solar masses. So it's a very peculiar low mass star that for some reason looks hot and looks high mass. In fact, Irgang et al. Noted that it has a very weird abundance pattern, and together with its low mass, they suggested that it cannot be a normal star, but rather a star that lost its outer layers, something that we call a stripped star, a star that somehow was stripped off its outer layers. And so for this reason, I'm gonna refer to this visible star as a stripped star in later slides. So coming back to the black hole, if we had this equation, which gave us the 70 solar masses, we know that we can neither trust the ratio, nor can we trust the mass of the B-type star. And therefore, there is absolutely no basis to thinking that there is a 70 solar mass black hole in here. So what is going on in this system? At this point, people were still thinking that there could be a black hole in here, just not as massive, or potentially a neutron star. To get more insights, we performed an algorithm which is called spectral disentangling. Spectral disentangling is a mathematical tool that takes a bunch of composite spectra like these ones, so spectra that contain the signatures of different components. And by plugging it into this tool, which can have different formalisms, which I won't expand on, you get a separated spectra. So basically a spectrum per stellar component. If you have a binary, you'll get 2 spectra out. One of the big advantages of doing that is that you strongly boost your signal to noise. So you get spectra out. It's kind of like co-adding all the observations. It really boosts the signal to noise of the spectrum. To do this algorithm, or this algorithm generally depends on the orbital parameters. If you adopt a certain period, you'll get certain spectra out and so on. But you can imagine that you can repeat this process iteratively. If, for example, I adopt a period that is wrong, I would get certain spectra that would not be as good in reproducing the data. And so you can construct kind of a chi-square map, seeing how well the data are reproduced by assuming different orbital parameters. So this is precisely what we did here. We know the orbital parameters already. We know the period, we know the eccentricity, we know the amplitude of the star that we see, the stripped star or the B-type star. The only thing we don't know is how rapidly the disk is moving in antiphase, if at all. We don't need to assume anything about the disk or about the nature of the component, except that it's moving in antiphase to the star that we do see. We use two independent methods to do that, one that relies on Fourier space and one that relies on wavelength space. And we basically got the same result independent of the method. And here you see an example for such a chi-square map, normalized in this case. So for different spectral lines, especially the age alpha line, which is this green curve, you see that a clear minimum is obtained when you assume that the disk is moving with an antiphase radial velocity amplitude of about 11 kilometer per second, which is about a fifth of the amplitude of the star that we do see. When you take this value and plug it in the disentanglement tool, you get two spectra out. And this was where the big surprise was to us. So I don't know if all of you are excited when you see spectra, but we were excited. So I have to spend some time on this. I'm going to start with the first spectrum, which belongs to the star we've been seeing all along, the stripped star or the B-type primary. So this is the red spectrum you see here. It has very narrow lines, very, very narrow, which implies that it's a very slow rotator. By analyzing the spectrum, we found that it's helium rich. It has, like was suggested before, a peculiarly low gravity, which implies a spectroscopic mass of the order of 1 to 2 solar masses. It has very strong nitrogen lines, implying that it's nitrogen rich. And it also has these weird, funny emission features in the Balmer lines, which I won't get into, and we're actually also working on this with Jon Sundquist's group. I currently think that these are primarily disk features, but probably entangled with other things. So we think that there is potentially a disk around this stripped star, not the main disk that we were seeing, another disk, but this is complicated. I won't enter this for now. The big surprise here was actually the second spectrum, the blue spectrum. Well, we knew that we're going to see disk features in the other spectrum, and indeed we retrieved these features. The big surprise was seeing these broad stellar features as well. So in the individual spectra, we were not able to see these features because of the signal to noise. But when you do the disentangling, these features pop up, and they're very evident if you look in the entire spectrum. So there's clearly another star here, and there is a disk around the star. So there is no black hole, but there is actually a disk around the star. And the reason these stellar features are so broad is because the star is a very rapid rotator. So if you're bored by staring at the spectra, this is the equivalent image of what we were seeing. We found that the companion is not a black hole, but rather a rapidly rotating B star with a disk. These stars have a name, they're called BE stars. And indeed about 20% of the B-type stars are this type of stars. So we find that this BE star has a mass of approximately 7 solar masses. It rotates basically as fast as it can. What we call a critical rotator. And the companion is, like we said before, has qualities that correspond to a stripped star, a star that somehow lost its outer layers. It has a mass that we estimate to be about 1.5 solar masses. So just to stress it again, it looks naively like an 8 solar mass star, but it actually, when you measure the mass, it has a mass of about 1.5 solar masses. And it's a very slow rotator. And like we said, the stripped star potentially has a disk of its own around it. So how do we understand such a funny system? Well, we know that the majority of massive stars actually don't live as single stars. They live in binary systems such as this one. And stars, as they evolve, they tend to expand. Now, in a binary, you're going to always have the primary star, the more massive star, and it will evolve more rapidly. So it would be the first to start expanding. The problem is that if it has a companion next to it, it cannot simply arbitrarily expand and become a red supergiant, but rather on its way, it would hit its Roche lobe, at which point it would start transferring a lot of mass to its companion. So at this point, the primary actually becomes a stripped star. It loses its outer layers, becomes hydrogen depleted, and the secondary becomes a very rapid rotator, potentially forming a disk around it. And there's actually a mass inversion. So the secondary becomes the more massive star. We think that LB1 represents exactly such a phase shortly after mass transfer. We see clearly the presence of the BE star, and we also see clearly the presence of a stripped star. The only funny thing about the stripped star is that it's not as hot as one would expect. These stripped stars are expected to be very evolved and helium burning, and they're typically very compact. This one isn't that compact. It isn't as hot as one would expect, which is why both we as well as Irgang et al. Before us suggested that it's not yet a helium burning object. It's a thermally contracting stripped star. So it's actually representing a very rare evolutionary phase. If we fast forward the evolution of LB1, we expect after a few tens of thousands of years that the stripped star would settle on the helium burning main sequence and would become an object that is called O subdwarf. So these are known types of objects. They're helium burning, hot, compact objects. And in fact, such binaries of O subdwarfs plus BE stars are known. And they're rare, they're very hard to detect, but they are known to exist. For example, Phi Persei and Omipup are such examples. The special thing about LB1 is that the mass that we derive for the stripped star seems to potentially exceed the Chandrasekhar limit. If this is the case, this means that it could be a supernova progenitor, making it really a one-of-a-kind detection. This means that the future evolution of LB1 could look like this. So the stripped star could actually explode as a supernova, leaving behind a neutron star. Such a binary can then become a high mass X-ray binary as the primary transfers mass to the neutron star. The objects could merge, form a Thorne-Zitko object. And if for some reason two supernovae occur and two neutron stars are born and the system remains bounded, it could also be a gravitational wave progenitor. So there is a zoo of phenomena that one could explain with an object such as LB1. So this concludes it for LB1. I will be quicker about the other system, this triple system. You may remember from the beginning, HR6819, that was claimed to be the nearest black hole to the sun. Of course, when we heard about this detection, we were too tempted to not try and run our tools on this system. And it turns out that we, again, cannot confirm the presence of a black hole in the system. This time we're talking about a much brighter star. It's actually visible to the naked eye. It's very close, well, comparably, relatively close to the Earth for a massive star, only 350 parsec away. And because it's so bright, it's been well studied before, and it's known to be a binary with a period of about 40 days. But the nature of the binary is not clear from the literature. It has different spectral types. And very recently, Revenius et al. Claimed it to be a triple system consisting of a BE star, so this star, rapidly rotating star with a disk that is moving in a very long period orbit around an inner binary. And this inner binary comprises a B-type giant. So again, very similar to LB1, a star that looks like a B-type star, and a black hole companion. So now you're all experts in these kind of plots, so I don't need to explain them as extensively. Basically, for this system, you see exactly what you see for LB1, only that here we have much more high quality data. No offense to Hermes, but it's also because it's much brighter. So it's Pharos data. And you can clearly see the absorption of one star moving back and forth with reported period. But the difference to LB1 is that you can also immediately see the presence of very broad absorption here, which you now know implies the presence of a very rapid rotator in the system. So we know that we have two stars here, one that is moving and the very rapid rotator. You can also see this configuration in other lines. For example, looking at iron 2 lines where you see this emission, which is characteristic of these BE stars, these rapidly rotating stars with disks. And of course, you have the infamous Balmer lines, which show the typical disk emission. So there's no doubt that there is a star that looks like a B-type star naively, and a BE star, so a star with a disk, in the system. And the obvious question is, aren't they binary components, just like in LB1? Well, Revenius et al. Claimed that they cannot be because the BE star doesn't move. If you look at the features of the BE star, it looks like it's static, like it doesn't move. They unfortunately don't provide any analysis to directly support this. This is promised to be in prep, but just by looking at the spectra, you can understand why they would think that, because it indeed doesn't seem to be moving. And if it doesn't move, then it must mean that this star is some kind of a very distant object, and that the thing causing the motion of the B-type star back and forth must be yet another object. And from dynamical arguments, they estimate that this object must have at least 4 solar masses, So very similarly to LB1, basically, if you don't see a four solar mass star in the system, it must be a black hole. So there again were a few critical points in this line of argumentation, but we, of course, now after working on LB1, the first thing we wanted to test is whether it's even necessary to invoke a black hole. Can't we simply check whether the BE and this other star are bound to each other? And that's exactly what we did. We used exactly the same methods as before. We used spectral disentangling. We assumed that the BE star is bound in the 40-day orbit, and disentangle the spectra as a function of its radial velocity amplitude, just like before. If our results would suggest that best results are obtained when we assume that it's static, that its amplitude is basically 0, then we would support the idea that it's a triple system and that this BE star must be a tertiary. But if our results suggest that the amplitude, or we get better results when assuming that the amplitude is larger than 0 by some significant amount, then we would conclude that this is a binary. And this is exactly what we did. Here we have much higher quality data, so we could really use about 20 different lines. And no matter which line we used, we basically found the same result. We found a minimum at approximately 4 kilometers per second for these chi-square maps, and no matter which line we used. So basically, it means that we get the best results when we assume that the BE star is moving in antiphase with this low amplitude motion. A weighted mean of all the measurements indeed yields precisely 4 kilometers per second with this error. And of course, this is a very small value. So immediately the question arises, can we trust this? Is this real? We have tried our best to simulate this. We actually created mock spectra, ran our tools on them, and everything seemed to suggest that this is real, and this is discussed in the paper as well. So this paper was led by my colleague, Julia Bodensteiner. We basically found very similar results to what we found for LB1. You can see the disentangled spectra here. Again, we find that the absorption line star, so not the BE star, but its companion, has properties that are consistent with it being a stripped star. It's a very nitrogen-rich star that has a very low spectroscopic mass. These results were confirmed by 2 independent studies that followed, basically to a scary level of accuracy. So basically, we started off with 2 systems where black holes were claimed. We actually suggest that these are not black hole systems, but actually very rare evolutionary phases of these BE binaries. This is a summary of the most important properties of the systems. You can see that they're very similar. One of the interesting differences is that the stripped star in this system, in HR6819, is of significantly lower mass than the stripped star in LB1, but there are some errors to that as well, so one needs to remember that. There are some other differences. For example, the stripped star in HR6819 is a very significant pulsator, something we do not see in LB1. The mass ratio in this system is much more extreme, and in HR6819 we also do not find a very clear indication for helium enrichment, which we did find in LB1. This is not that clear, however, because another group does report helium enrichment. So it could be also a little dependent on the model that we use. And this is still something that needs to be established. So I would like to conclude by iterating on the main astrophysical importance of these discoveries, starting with BE stars themselves. So like I mentioned before, these BE stars, these B-type stars with disks, are quite common. In fact, about 20% of the massive stars, which tend to look like B stars, have these disks and tend to exhibit this rapid rotation. And the question is why? Where do they come from? One of the ideas that started to propagate over the last few decades is that it's related to binary evolution. Just like you've seen in the animation I showed you before, a star accretes mass from a nearby companion, becomes this rapid rotator, and so on. But this is just one out of 4 or even 5 different scenarios that we have to explain the formation of these systems. The question is, of the stars. And the question is whether or not this is the dominant channel of forming this type of stars. So in this context, I would like to mention another paper that Julia, Luxana, and myself have published about a month ago, which focuses on this problem, where we actually it was just a literature study, and we just note the fact that of all the BE stars, you never seem to find BE stars that have main sequence companions. If you look at this cartoon, you see that this is precisely what you expect if the binary evolution, the binary channel is indeed the dominant channel. So you see that when the BE star is born, it always leaves near funny stars like the stripped star or a neutron star. They never leave near main sequence companions. And indeed, we find very strong indication that this is the case when you look at the real data, but this is still something we're working on. So finding systems like LB1 and HR6819, which represent very rare evolutionary phases that fit somewhere here, where I put the square, gives us another indication that this must be a very common channel, because these are rare phases, and this must mean that this channel as a whole must happen quite frequently. These systems are also related to a completely different subject of research, which is stripped stars. So they are getting hyped, especially over the last few years. It has been realized because massive stars are so, massive binaries are so common, that these stripped massive stars should be also common. There should be hundreds of thousands of them, or maybe tens of thousands of very massive ones in our own galaxy. The only problem is that they were never observed by direct means. They are expected to be the main progenitors of supernovae, stripped supernovae, and they were also suggested to be a very important source of ionizing radiation, but we have not yet been able to really detect them by direct means. So LB1 potentially represents one of the only cases where you see a stripped star that exceeds the Chandrasekhar limit, that is not a Wolf-Rayet star, so these very massive rare stars. And we hope that this could give us a hint, or let's say a first step on a long process of trying to realize whether these stripped stars are as rare as they seem to be, or whether this is an observational bias. I usually start my talks by saying that binary interaction dominates the evolution of massive stars. This became quite usual in our talks. So these kind of binary interactions are indeed the rule rather than the exception. Most massive stars undergo these kind of interactions. There are a lot of physical processes that are related to those that we do not understand well and do not have good calibrations for. And by studying such post mass transfer stars, such evolved binaries, we can actually constrain, it's the only way we can constrain and validate our models of binary interactions. And finally, I promised to talk about black holes, but then black holes seem to evaporate. So where are they? In fact, we do expect that there should be a very large, a very significant amount of black holes out there. In fact, a recent study suggests that 2 to 4% of the massive stars should have black hole companions that are not accreting in X-rays. And yet the detections of black holes are really, really sparse. And even the few that were detected are still under debate. We believe that many more should be out there, and if not, this means that something is awfully wrong in our models. This should definitely be verified by observations, and I hope that in the coming years, we will be hearing more and more about black hole detections. So I would like to summarize. First of all, if you don't know these people, this is Ug's group, and like I said, all the results that you've seen today were obtained through collaborative efforts with all of this group. We started by talking about the fact that the most massive stars ever observed seem to reach a robust upper limit of about 150 solar masses, but could be as massive as 300 solar masses in the local group. But the problem is that at least in our galaxy, these stars are expected to end their lives as 10 to 20 Wolf-Rayet stars, which is why it was such a big surprise to find a 70 solar mass black hole right in our own galaxy. I hope I could convince you that LB1, however, does not contain a black hole, that in fact it represents a rare evolutionary phase of a BE binary. We suggest that the same model applies to HR6819. It's not a triple, it does not contain a black hole, but it represents this rare evolutionary phase. I hope I could show you in the last few slides, this has significant consequences for binary evolution in the context of the origin of stripped stars and BE stars. And finally, those black holes must be out there, we believe, and I encourage everyone to try and go and find them. We should just be careful about the bias that we have in wanting to find them, and challenge ourselves as best we can in this context. So this I will end. Thank you.
Thank you very much, Tom. It was a very nice talk.
Thanks.
So yeah, I suspect there might be some questions. So if you have a question, please post in the chat your name or just mention that you have a question, and then I will tell your name and you can ask. You unmute yourself and you ask the question. Does anyone have a question for Thomas? It was very clearly explained, so
or everyone just know all these results already. Maybe.
Join, please. Don't forget to unmute you.
I unmuted myself, huh?
Great.
Yes. Excellent. Very nice talk, Tomer. I thought I could just start off. I'm sure that more questions will follow. Actually, I had two small questions. One is just something that is curious to me, because you talk about these stars. The suggestion is that they are stripped stars, right? Mm-hmm. But naively, I would expect that such stripped stars then would have lost their hydrogen envelope. Okay, so but all the detections are with hydrogen lines, right? So I don't, you know, I don't see how the so to say hydrogen to helium ratio. Is this something you have looked into? Yeah, sure. So we have constantly compared, especially with the help of Pablo Malchant, with predictions of what you'd expect for such post-mass transfer systems. You actually don't expect, in no case, you would expect the entire hydrogen envelope to be shed off. You always are left with some hydrogen on top. How much is considered an uncertainty, but it is expected, especially at the lower mass regime, that they retain a significant amount of hydrogen in terms of mass fraction that you see at the surface. So this is why it's not necessarily a problem. The detailed ratio of helium to hydrogen is more of a challenge. Yeah, because to me, it seems like, to be honest with you, it seems a quite big challenge in this basic scenario, but I don't know what type of abundances you get, but just looking at the helium versus hydrogen lines, it seems to be, I don't know how enriched, so to say, it is in helium. So in LB1, we found a helium abundance, I think, of about 40%. If Julia is around, maybe she remembers. Okay. Well, that's significant then. So that would be. Yeah, so it was, for LB1, it was a significant enrichment. Whether it's exactly what you would expect from models, it depends on which model you look at. For the other system, it was more challenging because there we could not find clear indication of enrichment, as I mentioned. Unlike the other independent group, we have a bunch of models trying to explain this discrepancy, and it's an interesting discrepancy. But I don't see how else to explain all the properties of the star. So everything about it suggests this. No, it was just something out of my curiosity. And then the second question I have is just about this origin of these, and I would like to hear your opinion. I mean, as you know, one of our other specialties here at Leuven is to predict these mass loss rates, right, that you talked about in the beginning. And I know that you're very well aware of that if we apply our new Leuven recipes instead of those that are currently included in codes like bypass and MESA, we have lower mass loss rates for at least in the blue parts of the HR diagram. But that also means that when we look at the evolution models, we actually don't get so many of these Wolf-Rayet stars at the high mass. We have to go up to very high mass. So that's the first thing. At the galaxy, about 100 initial masses. So then I would just ask you, is that compatible with your opinion in the observational sense? And then two, also, indeed, we can predict these type of very high mass black holes. Actually, a study was done by this year by Rafael Hirschi and Beltsinski, where they just scaled down the mass loss rates in current MESA models, and they ended up with galactic black holes on the order of 70 solar masses. That was, of course, before you guys published your counter arguments to why this Nature paper is held. But the point is that the so to say the type of downward scaling that they applied are pretty much what we find in our updated mass loss recipes. So then again, I would just ask you perhaps about your opinion that, yeah, again, where are all these black holes? But also I would estimate that we should find also quite high mass black holes also in our galaxy.
So I would try to break down the problem. First of all, because you started with Wolf-Rayet stars.
Yes.
I do not think, at least naively looking at the galactic population, I do not think that it's consistent with, if you say like only 100 solar mass stars would end up becoming Wolf-Rayet stars, single stars, you need to go crazy with scenarios in explaining why we see so many single Wolf-Rayet stars at much lower masses. So naively, it's not consistent. I think, and it's related to your second question as well. I am, of course, very aware of your results. Correct me if I'm wrong, but these results currently correspond primarily to the main sequence mass loss, right?
Well, I would say actually, yes and no. We can extrapolate them with quite a high level of confidence to also the post-main sequence until you basically reach something like, you know, below 10,000 Kelvin.
But can you extrapolate them to Wolf-Rayet stars and to red supergiants?
No, I mean not to the classical Wolf-Rayet stars. But the point is that you don't get over.
Yeah. So that kind of also would be the answer to the second question. As you probably know, the mass that is lost by a massive star is primarily dominated by the mass loss during the red supergiant phase, or during the Wolf-Rayet phase, or during both. And for these phases, it's not. So I think there is very strong evidence, as your work also shows, that mass loss rates on the main sequence are lower than what we thought before. But as this was not the major contributor for the mass loss of massive stars, it still doesn't really resolve the problem of how you can form such massive black holes. Of course, I could crunch down the red supergiant mass loss rates and the Wolf-Rayet mass loss rates, but this is not really supported right now by either observation or theory, as far as I'm aware.
No, but the point is that with these massive stars, you never get over to the red supergiant branch.
So, okay, I mean,
so
you never get.
You don't have like an 80 solar mass red supergiant, or at least we don't observe them, right?
Yeah, so you remain all the time in the parameter regime where your models you would think are valid.
Yes.
That's what I see your point. It's an interesting point. I think, like I said, that the observed distribution of Wolf-Rayet stars makes it very challenging.
Yeah. Okay.
It still needs to be seen whether it's, you know, it's all binaries and stuff like that, but it's you know, if we would observe a 70 solar mass black hole in our own galaxy, I would want to brainstorm with you on how we can do that. But it's definitely a challenge to standard models. Let's put it.
No, I agree. Actually, I mostly wanted a little bit of your input into and your expertise into this question. I agree completely. It's very challenging.
Okay.
Thank you. Very nice talk.
Thank you, John.
Thanks.
Maybe I will first give the opportunity to the junior people to ask questions. So Dylan, please.
Hi.
Hi.
Very nice talk. So as you know, in your work here, one of my particular interests is these origins of classical BE stars. And so I'm curious, based on the fact that if you have two of these stars in this extremely rare phase, I mean, of course, this is extrapolating from small number statistics, but is that, what sort of constraints does that place on the relative fraction of classical BE stars that would have to form via this pathway or could still be from another pathway?
I think that's a very good question. We haven't looked into that. My feeling is that it gives very strong constraints, but I would just have to invent numbers.
No, that's fine. It seemed like it to me too, but I just was curious if you looked at it.
Yeah, so no, not yet. And yeah, it's a very good thing to keep in mind and to check, indeed.
Great. Well, keep me posted. I'm very interested, of course.
Okay.
And then David, do you also want to ask your question? You may have to unmute yourself.
I'm curious if in so many systems there are possibly less black holes, but you're still certain that they're around, what kinds of systems do you think you'd most likely find them in?
So you can find black holes in all different types of systems, and you can find them near low mass stars, for example, and that's a whole different riddle how you find them. But as a massive star person, well, you want to look for massive stars that have a companion. This means that these massive stars are going to move around, and they will probably look like SB1 systems. So systems where you only see a single star moving back and forth, and you don't see the companion. And this is a promising place to start. The problem is that there could be a bunch of different types of companions that you don't detect. Maybe it's a low mass star, maybe it's a neutron star. So it takes a lot of work to find those. But any massive star could have a black hole companion, basically.
Okay.
Great. Andrew, you also had a question.
Yep, thank you. Thanks, Tomer, very nice talk and impressive results. I have a somewhat technical and therefore boring question than other questions here, but I find it very important because you kind of rely on your derived atmospheric parameters to predict the future evolution of the system, right? And you even make a mass estimate of the streep star based on those parameters, starting from those parameters essentially. And the way you get them is through spectral disentangling, right? So the doesn't matter which way you disentangle the spectra, either in Fourier space or in wavelength space. The basic assumption is always that the only variability that you observe in the spectrum is due to the orbital motion. Correct. Now, I can't imagine that the BE disk is homogeneous slash unclumpy and that kind of stuff. So I wonder how much of the line profile variability, either in emission component spectrum or in absorption component spectrum, would influence your spectral disentangling and therefore the interpretation of the spectra that you're obtaining. Because I think that that might have a major influence on your mass and further evolution estimates.
Okay, so first of all, it's a very good question, and indeed technical but very important, and not necessarily easy to answer in this framework. You're right that the method assumes that the only variability originates in orbital motion. If you would have stochastic variability of some kind, and you have a lot of spectra, and you would perform this method, as long as this variability is stochastic, it would kind of smear out, and it might introduce some kind of an excess on some lines depending on the strength of whatever it is that is varying. Typically it's not going to be important. As a spectroscopist, you usually also want to look at the individual spectra, and you see, you know, for example, an absorption line belonging to one star, you see it moving, and maybe every now and again it has a slight, I don't know, clump traveling on it, but then when you co-add all the observations, these things kind of disappear. So for some spectral features, it's not going to be important. For others, like the Balmer lines, where there is a lot of mess, it can definitely be important. I think that the most important consequence it could have on the spectra are, first of all, the exact value of the radial velocity amplitude, from which you get the mass ratio and one of the mass estimates. And the second thing is the appearance of the Balmer lines, what we've discussed before, these emission features and so on, which we have discussed this privately a lot with Yun, why we think there is a mission where we see it, but where we should be careful by overinterpreting the disentangled spectra. I will highlight the fact that the mass, for example, the mass estimates come from two independent methods, one of which is measuring the two radial velocities and therefore getting a mass ratio constraints and estimating, calibrating one of the masses to get the inclination. And the second one is the spectroscopic mass, and in this case, they both agree actually very well. I do not see a reason why these mass estimates should be very far off because of disentangling. Just from experience and from looking at the individual data and comparing the disentangled spectra to the individual spectra, you can
yeah, thank you. And sorry for asking, but what do you mean by spectroscopic mass? Because as Joris noticed I'm a bit old-fashioned, and to me that could mean different things.
Okay, sorry. So spectroscopic mass is to me what you derive directly from the spectrum. So you get the gravity from the spectrum, you get the temperature from the spectrum, and you get the luminosity by fitting the star to an SED. By constraining all these parameters, which have their associated errors, you have the radius, you have the gravity, you have, that's it. You have the radius from Stefan Boltzmann and the gravity from the spectrum. And that's how you get the spectroscopic mass. This is what I mean by spectroscopic mass.
Yeah, thank you. So I'm not sure how long your time series of spectra is, of course, for LB1 system, but maybe just to test the impact of disentangling, would it be enough to, let's say, eliminate 5 to 10% of spectra from your entire time series, and then repeat spectral disentangling and do that, let's say 10, 50 times, right? Just to see how much of an impact a random elimination of 10% of your data set will have on the final results.
It's a good test. It's an interesting test. I'll forward you the observations and then you can do it.
Sure.
Okay, maybe we can go to our very last junior person, Hans van Winkel, if you have also a question.
Thank you to call me junior, very good. I have a question with respect to LB1. So the stripped star is not in equilibrium, but what is the time scale to bring that star into equilibrium? Because I thought it was very fast. That means it is very, very rare.
So the estimates that we have done back then were of the order of 50,000 years. So I don't know what you would call, as a low mass star person, this might sound like very fast to you. As a high mass star person, it doesn't sound that crazy fast to me.
No.
So it's a scale that you can observe if you're lucky, but of course it's rare. Yeah. And by the way, this is the current interpretation. It's actually, the more I talk to stripped star people and the uncertainties on models, the more I understand that it's potentially not as clear, for example, how puffed up stripped stars will be. It depends a lot on how much hydrogen they have. And this is our current interpretation, that it's a thermally unstable stripped star because of its properties, but it may not be the final verdict.
Okay, thanks.
Okay, then that leaves me with thanking Tomer again. So we can't really clap now. Well, we can actually with the reaction button, but you will not hear a lot. But thank you again, and I hope to see all of you next week. So we will have a new seminar, probably also with Zoom, and I'll see you then.
Thank you, guys. Bye-bye.
Okay, thank you.